About quadratics. So, quadratics are the most common type of line outside of straight lines. We actually see them everywhere. So, it says here year 10, you guys started learning about them in year 9, but I doubt many people remember them from then. There's I believe in the year 9 test, there's a single quadratic question. The shape they produce, called a parabola. Oh, my pen's... There we go. Your parabola is an everyday feature of life. So, when I say a quadratic, I'm referring to the type of equation. When I talk about parabolas, I'm talking about the shape of the graph. So parabola is just the shape of the graph. Shape of the graph. I do apologize if my handwriting's worse than normal, but I'm doing it on the vertical screen, which isn't great. So, parabolas are something that you see all over the man-made and natural world. It turns out they're one of the most sturdy shapes for building. So you see lots of arches doing the parabola shape. The ancient Romans in the aqueducts used them. Any object that is thrown. So if I throw this remote control at Zoe Higginbotham up the back, it's going to go in the shape of a parabola. Dolphin leaping out of the water, that's a parabola. The giant radar dishes that they scan planets and stuff with, they're parabola shaped. Turns out it has tons of useful applications, these parabolas. You shoot water out of a bubbler, the shape that it comes out in is a parabola. There you go. Mathematically, parabola equations can look like a few different things. The most basic form of a parabola is y equals x squared. That's the most basic, boring one. Generally speaking, the general form of a parabola is y equals ax squared plus bx plus c. That is every single parabola that ever has or ever will be can be described using that second formula. Where just the a, b, and c values change depending on the individual parabola. If you have a look at our graph here, the blue one, it has the equation 3x squared plus y equals 5. Can you see that this rule, they're just rearranged versions of each other? They haven't kept the y separate from the x. Generally speaking, we're always going to keep the y's and x's separate because it's easier then to plot and graph and solve. Yep. So when you say positive, so you make a good point. In a parabola, a upwards facing parabola, or what we call a smiley. The way you know it's going to be a smiley, it has a positive a value. So if you look at the number in front of the x squared, the a, if it's positive, it'll go up. Now, Rylan made a good point. In the blue line there, everything is positive. So if I'm saying that it has a positive a value, it will be a smiley. How come the blue one's not a smiley? The bx doesn't matter. The bx just translates it, essentially. Can anyone see why that might not... Does it have a hidden negative a value, perhaps? What do you think, Lachlan? The reason why is because y and x are on the same side. To get it into the general formula, y equals ax squared plus bx plus c, you'd have to minus 3x squared from both sides. You'd end up with y equals minus 3x squared plus 5. And then in that case, it would be a negative. So there we go. We call this one a frowny. Not like mathematically rigorous names, but you will hear me say repeatedly, is this one going to be a smiley or a frowny? Is it going to go up or is it going to go down? So a frowny has a negative a value. Plus VE minus VE is just shorthand for positive negative, just if you didn't pick that up. But yeah, those are some parabolas made by quadratic equations. Yeah, that's pretty much it. Let's have a look at some problems. Like I said, the most common way to represent the quadratic equation is with your rule. Y equals ax squared plus bx plus c. You might remember when we talked about linear lines, what's the general form of a linear? No, but like what rule do we use to represent everyone? Yeah, y equals mx plus c. So you've heard about y equals mx plus c since like year 8. The quadratic version of that is y equals ax squared plus bx plus c. So we're going to look at other ways of writing the rule. There are other ways of writing that you will come across, but you can always get it into that form if you have to. So each parabola has a number of features. We often call these critical points that help us describe a quadratic and help us solve problems around them as well. So each quadratic has its turning point. So this is where, if you think of a frowny, it starts going up and then it flattens out and then it starts going down. Smiley starts going down, flattens out, starts going up. So each quadratic will have that turning point in the middle of it. In relation to that, it also has an axis of symmetry. Every quadratic is symmetrical, perfectly symmetrical. So it's always symmetrical around the turning point. So if I go back up here to this one, can you see that my green parabola is symmetrical around that dashed line that I just drew? It's perfectly the same either side. There is a y-intercept. Each parabola will only ever cross the y-intercept once. The reason why is it's a function. So a function can only ever touch the y-intercept once. If it touched it twice, why would that stop it being a function?
Right.
Yeah, but why would it? If it touched the y-axis twice. So if we look at this one here, the blue one, say, if it, like, I don't know, skirted around and did that, it touched the y-axis there and there, it wouldn't be symmetrical, but why wouldn't it be a function? What test do we have for functions that it would fail the vertical line test. But yeah, it would not be symmetrical and it would fail the vertical line test. So there can only ever be one y-intercept. And there can be up to 2 x-intercepts. It can touch the x-axis twice. It can touch it not at all. So for example, if we go back up here, I could have a frowny like that, never touches the x-axis. Oh, it is 2. Or I could have a frowny like this, touches it twice. You could also have something that touches it at exactly 1 point. So you can have 0, 1, or 2 x-intercepts. Okay. So guys, let's have a crack. State the turning point, axis of symmetry, and all other relevant intercepts of the following parabolas. This first one here, where is my turning point? 2, -3. My axis of symmetry. Would you agree that this vertical line is my axis of symmetry? So we would say the axis of symmetry is x equals 2. Because it is symmetrical around that vertical line. X equals 2. So the way we would describe that vertical line is x equals 2. Remember when we're doing horizontal lines, it might be something like y equals 1 or y equals 3. And that describes a horizontal line. A vertical line is just what the x value is. X equals 2 in this case. Relevant intercepts. What intercepts do I have? Yep, and where does 1 and 3? X intercepts at, and for our x-intercepts, we want to give our coordinates. So the first coordinate would be 1, 0, and my second coordinate would be 3, 0. Yeah. And do we have the y-intercept? It's not shown to us, so we can't really say what it is. So it can be question mark. The question doesn't really ask for this, but I think it's worth talking about. If I was to say the domain of this function, do you guys think there's a limit on the domain, or would it be infinity, negative infinity to positive infinity? Is there anything stopping this function from going to negative infinity in the x direction? No. So let's say the domain is negative infinity less than or equal to x, which is less than or equal to positive infinity. All x values are possible. Are all y values possible for this function? Where would the cutoff for the y values of this function be?
I'd say like where
Yeah, can this function ever go below negative 3? No. So we'd say the range is, so the lower limit of our range, the lowest y value it can take on is negative 3, less than or equal to y, less than or equal to positive infinity. Because would there be any upper limit on how tall it can get? No. Does that make sense, guys? Cool. Let's have a look at these ones now. What's our first one we're doing? The turning point. What's the turning point of this one here? 0, 0. The axis of symmetry. What's my axis of symmetry here?
0. X equals 0.
X equals 0. That's right. We can't just say 0. We've got to give a line that it is reflected around. Do I have x-intercepts? Yeah, it'll be x-intercept at 0, 0. Same as the turning point. In this case, the turning point is the x-intercept. The domain would be the same. The range would be different, though. I won't. Yeah, it was just because it wasn't on the previous graph. We couldn't see it. Okay. We don't necessarily need to do the domain and range for these ones. I just wanted to get you in the habit of thinking about domain and range for these functions. For the final one, where's my turning point? Negative 2, 1. Axis of symmetry.
X equals negative 2.
X equals negative 2, excellent. My x-intercepts. Where are my x-intercepts? There are none. Doesn't cross the x-axis, so no x-ints. And my y-intercept looks like an S, doesn't it? 0, 3. My y-intercept is 0, 3. Oh, I'm not writing well today. 0, 3. Are we all feeling reasonably comfortable just at looking at those critical points? It's gonna become more important later on, essentially, as to why we need to know those particular things. We're gonna learn if I give you a rule like y equals 5x squared minus 2x plus 3, we're going to learn how to get those values just from the rule, not from just looking at the graph. Let's start now. So, finding critical points mathematically. When reading critical points of a graph is relatively simple. Sometimes you only have the formula. Following section, we're going to look at finding intercepts and turning points using some mathematical tricks. Some trickery. Easiest point is always the y-intercept. This is because you can simply substitute in x equals 0. Why would we sub in x equals 0 to find the y-intercept? Yeah, because the y-intercept always happens where x equals 0, because along the y-axis, what's x equal to? 0. That's it. So, to find the y-intercept for these, we just want to sub 0 into the rules. So, y equals -2, 0 squared equals 0. Therefore, y int at 0, 0. Would anyone like to hazard a guess without doing any maths whatsoever for the second one? What will the y-intercept be? Okay. 9. Why is that? Gut feeling?
Not quite,
because what are we going to sub in? 0. So what's going to happen to all the terms with x in it? They're going to go to 0. So the only thing that's ever going to be left over... Sorry? No, so the 3x squared, the x squared becomes 0. 3 times 0 is 0. The next one, the minus 12x, the x becomes 0. 12 times 0 is 0, so you end up with 0 minus 0 plus 9, which is 9. So let's sub it in. 3 times 0 squared minus 12, 0 plus 9 equals 9. So y int at 0, 0. Oh yeah, we're supposed to match them to the correct function as well. We'll do that at the end. So for this one here, same thing. Replace the x with zeros, or replace the x's with zeros, I should say. Oh, sorry, because I wasn't thinking. Should be 0, 9. Geez, I've been doing that all day so far. I'm not on top of it today. 3. So, if we look at our 3 graphs down the bottom, guys, the blue one on the left, which one do you reckon it matches, A, B, or C? C, because it's the one that has a y-intercept of 3. The second one, which one does he match? A, y-intercept of 0. And that leaves B, y-intercept of 9. For the third one. So, yeah. That's about as simple as it gets, guys. So, next we'll find the x-intercepts, find them a similar way, except we set y equals 0, find where the parabola touches. These ones are tricky, and I'm hoping to get you to solve these using your graphics calculators, not today, but later in the week. Who has returned their forms and that and got their graphics calculators? Excellent. So, we won't get to the tech side today, but you will need to probably by Friday, ideally, have your graphics calcs. Does anyone think they're not going to be able to get their graphics calculators by the end of the week? If you don't think you'll be able to get it, come see me and you might be able to find you a loan one or something in the meantime. Okay. Let's do this. Okay. We got 2 main ways of finding out the x-intercepts without the calculator. First is by factorization. The thing that everyone hated in year 9 and thought, when am I ever going to use this in my life? Turns out in methods. So we're going to do factorization. Okay, when we use factorization, this is really important. we only use it for what we call monic quadratics. A quadratic is monic if it's just, there's no a value basically, or the a value is 1. So it becomes too difficult to factorize otherwise. So who remembers factorizing quadratics in like year 9 or 10? Ashton? Yeah, a few of us? It's horrible. Okay. I'll show you the cheap way of doing it, guys. I know. Okay, I'll show you this way. If I start, let's use U and V. If I was to expand out those brackets, guys, if I was to expand out those brackets, use your fireworks or your foil, whatever you want to do. Oh, the first term. I should just explain the reason I'm doing this with letters is because this is how you do every single one. So I'm just using letters to show the process. If we expanded it out, we'd get x squared. And then we'd get xv. And then we'd get ux. And then we'd get... Oh my goodness. ux. Where's my erase button? And then at the end we'd get uv. Maybe I should have used the NV. Anyway. So we have x squared at the beginning, uv at the end. Now this uv and the ux have a common term of x. Oh my goodness. My brain's all over the shop. So you can see in this middle term, they both have that common factor of x. So I've factorized out that factor of x.
Excellent.
Normally you would. There's a reason I'm putting it behind here. And that's because if we look over to the left-hand side where we've got like 8 followed by the x, u and v represent numbers that we're basically going to find, whereas x doesn't. So, which is why I've put it towards the back. Can you see that this equation here, x squared plus u plus vx plus uv, it looks kind of similar to this one here. The one over on the left. We have an x squared, we have some number times by x, and then we have some number without an x. Do you agree that they look similar?
Yeah.
Yep. So, I'm going to say that if these two look similar, and I know that this bottom line is equal to the top line, I'm going to say that over here, I can factorize this to x plus u, x plus v. And we're going to find out what u and v are. So what I said is, okay, I've linked this line here to this end line here because they're set up the same way, x squared plus something without x. And no, I haven't touched the x squared. All I've said is this line here is equal to what I started with. So all I've done is well, that equals to that, which equals to that. And I've skipped the middle step to just plop that there. Now, we know that because this line here, I'm going to call it number 1. Because number 1 is equal to number 2, what can I say about u plus v? What does u plus v have to equal to in this case? Not 12, you're on the right track. If we match up in number 1 and number 2, where the u plus v is, it has to equal 8. So I can make the call that u plus v equals 8. What does u times v match up with? 12.
So can you fix that 8?
Looks more like an 8 now. So all we've got to do is figure out what numbers add to 8, multiply to 12. So let's look at the factors of 12. We've got 1 and 12. They add to 13. No good. 2 and 6. They add to 8. And I'll just say 3 and 4 as well, but they add to 7. So the only two numbers that multiply to 12 and add to 8 have to be 2 and 6. So I can therefore say x plus 2, x plus 6 is my answer for factorizing that one. Just to prove I'm not tricking you, let's expand it out and just check that we get back to x squared plus 8x plus 12. Yes, you can. The reason I'm showing you this, guys, is just to show you how we get to this step. At the stage you guys are at, I'm fine if you say, if you can in your head go, they've got to add to 8 times to 12 and figure it out. But I will keep doing it this way just so you can see how we're getting to that answer, because often people get lost in that, oh wait, where did this 2 and 6 come from? I don't get it. So I'm just going to expand these out just to prove that I'm not a liar this time. X times x is x squared, x times 6 is 6x, 2 times x is 2x, 2 times 6 is 12, x squared has nothing to add to, 6x and 2x can become 8x, and 12. Bish bash bosh, they're equal to the same thing. Now, why did I want to get it in the form of 2 brackets? What's my end goal here? What am I trying to do? Not to plot it, but to find what the x-intercepts. And where do the x, that's where it crosses the x-axis. Where does the x-axis happen at what value of y? So if we go back up, if I go back up here, my x-intercepts always happen at what value of y, no matter what the quadratic? 0. So, to solve for x-intercepts, set y equal to 0. And I know y is on my left-hand side of the equation over here. So I end up with 0 equals x plus 2, x plus 6. Now, would you believe me if I said to you that's actually super duper easy to solve?
Yep.
Ashton does. He's on Team Parker. He believes in me. The reason why it's easy to solve, guys, is because something called the null factor law. And the null factor law is, guys, if I want to make the right-hand side of my equation 0, if I make the first bracket 0, what's going to happen to the whole equation? It'll be 0, because 0 times anything is 0. What if I make the right-hand bracket equal to 0? What will happen to the whole equation? 0. So the way I solve this is I either make the first bracket 0 or I make the second bracket 0. Both answers are correct. So in this particular case, there's 2 answers. How would I make the first bracket 0? What would x have to be to make the first bracket 0? 0 plus 2 is equal to 2. Negative 2.
Yeah.
And then the second bracket? Yep, so x equals negative 2 and negative 6. Because remember, we're allowed to have up to 2 x-intercepts for a quadratic. That's it. Those are our x-intercepts. I should probably say, therefore, x-intercepts at -2, 0 and -6, 0. What was my original equation? X squared plus 8x plus 12. Let's just prove I'm not a liar. Let's go to Desmos. Okay, guys, have a look here. If we put in my original equation, y equals x squared plus 8x plus 12, where are the x-intercepts? -6, -2. This is what is so great about maths. The graph matches the maths matches the graph. You can always check your answer. Cool. Before I move on, who thinks, having looked at that one, they'd be able to do another one on their own now? Ryland's all over it. Elizabeth is kind of all over it. Sky's all over it. Good stuff, guys. Whoa. I honestly was trying to. So, guys, like I said, in a normal question, I'm happy for you guys to go from straight to probably do something to show you working out. Like if you go x plus u, x plus v maybe as you're working out. Next step, put your numbers in, set 0. So you can sort of do this in like 3 steps of working out. I've used a lot more just to show you why it works, but you don't need to use that many. Okay.
That's right.
When it's a minus. But this is why we look at the factors. We will do this one together, but I'll get you to do... see how we go. Okay. Before we go, are you guys looking at the next questions? Okay. You are right. You will remove the 3.
What?
You factorize out the 3.
Yeah.
Okay, but let's look at this one, guys. So I know y has to equal x plus u, x plus v. Now, because this one has a negative in it, I'd actually honestly encourage you to do a little thing off to the side, just looking at your factors. Because I know x plus u equals -5. X plus u. Oh my goodness. V times u equals 6. Let's look at the factors of 6. We have 1 and 6. They add to 7. We have 2 and 3. They add to 5. This is an issue because neither of those factor pairs add to -5. So am I missing any factors of 6? Yeah, because a negative times a negative is still a positive. So the negative versions of these will also work. -1, -6. So -1 plus -6 is -7, no good. -2, -3. Oh, they add to -5. So y equals x minus 2, x minus 3. Make sense, guys? Sweet. What? Sorry? So the top one is v plus u, the bottom one is v times u. So if my first bracket is x minus 2, according to the null factor law, what do I need to make x to make it the whole thing 0? Positive dose. So x equals 2 or 3. So it has an x-intercept at 2 and x-intercept at 3. Or 2, 0, 3, 0. Okay.
Where you wrote 0 equals x negative 2.
Minus 2 or negative 2, yeah.
Yeah. And then x negative 6, and then you wrote x is 2 or 3.
Negative 6, negative 3.
Sorry. But on the next line is a negative.
Because what we're trying to do is make either the left-hand bracket or the right-hand bracket equal to 0. So if we look at just the left-hand bracket, x minus 2, the way we make that equal to 0 is if we made it x equal to negative 2 minus 2 would be negative 4.
Oh, yeah.
So it'll basically always be the opposite of whatever's in the bracket. So it'll be, positive 2 or positive 3, make it equal to 0. Okay, any questions on that one, guys? Yo, are you looking at the third one? We're about to do it.
You're. No.
Sorry, you don't be.
So that's
You're working out is behind a graph, but you've ended up getting 12x. So what you haven't done, so the reason why you was defined is you divided by 2, but you haven't divided by 2. But it ends up working out as y being subbed in 0 so it doesn't matter. Yeah, but you haven't should that. What do you try that? 0. Because you sub in, so y would divide by 2 would be sub into the 0. Same thing up here, where you sub in y equals 0, and then you divide everything by 3, and 12, that's 36. Okay, guys, let's do B.
White crew.
Actually, is there textbook work at the bottom of this one? No. It's alright, we'll do some textbook work on this Thursday. We're going to do B. B is a bit trickier. Can anyone point out why this one is trickier? Lachlan. It has... I can't hear what you're saying. Like a negative. That does make it more difficult. That's not the worst thing, right? Yeah. So, guys, what makes this one trickier is it's what we call non-monic. So there's something in front of the x squared that we don't want there. So we're going to have to get rid of it. To get rid of it, I'm going to do something. There's 2 or 3 ways you can go about getting rid of it. Just thinking what the easiest way to do it is. I'm going to factorize it out because I want nothing in front of that x squared. So if we look at the right-hand side, is there a common factor between all those terms there? Yep. What is it? 3. So I'm going to say, well, that's equal to y equals 3 outside of x squared because I factorized out the 3. When I factorize out 3 from negative 12x, what's left over? When I factorize 3 out of negative 12x, what's left over? 4. Or negative 4x, I should say. When I factorize 3 out of negative 36, what's left over? Negative 12. Now, we do have a dilemma. That 3 is still there. We haven't got rid of it yet. To truly get rid of it, we're going to have to sort of jump a step forward. Normally, I don't sub in y equals 0 till later. But I'm going to sub it in now. The reason why is I'm going to divide both sides by 3. And what's 0 divided by 3? 0. So that essentially turfs that 3 out of the equation. We don't need to worry about it anymore. So I'm going to sub in y equals 0. So 0 equals 3 bracket x squared minus 4x minus 12. Then I'm going to divide this side by 3, divide this side by 3. 0 equals x squared minus 4x minus 12. Then I can say, okay, well that equals x plus u, x plus v. And I want a u and a v such as they add to -4 and they multiply to -12. Now, -12, whoops, we could have 1 and 12, 2 and 6, and I'd say that's going to be the one. I'll just explain my thought process here, guys. Because they both multiply to a negative number, what can I tell about the signs of my two numbers? One's positive, one's negative. The second thing I know is that they add to -4. So that says to me that the difference between them is 4. And the bigger number is the -1. So if I look at the factors of 12, 1 and 12, 2 and 6, 3 and 4, of those factors, which one has a difference of 4? 2 and 6. And the bigger number is the negative because when you add them together, they become a negative overall. So that tells me that the factors I'm looking for are 2 and -6. Does that thought process make sense, guys? Yeah. 2 times -6 is -12. 2 plus -6 is -4. So that gives me my values. X plus 2, x minus 6 equals 0. So therefore, x equals -2 or +6.
The matter can't go like switch around.
Like if you said x equals 6 or -2, or if you got those signs the other way around.
Like negative.
If you did it that way, you done it wrong. +2 take -6 is -4, which is what we want. Ryland?
Last part, you like, yeah, between -6 and then just switch it around.
Yeah, so I might do... I'll do it here. I wish I had access to other colors here just to make it easier. So we've got 0 equals x plus 2, x minus 6, right? So I'm going to make the claim that x equals -2 makes the equation true. So the left-hand side equaling the right-hand side. So I'm going to sub in x equals -2. Null factor, yeah. So we've got 0 equals -2 plus 2, and then -2 minus 6, right? 0 equals, in the first bracket, what's -2 plus 2? 0. And then what's -2 minus 6? -8. 0 times -8? 0. So 0 equals 0. Therefore, x equals -2 is a solution. So I've chosen a value that is going to turn one of my brackets into 0. See that if I did the exact same thing, but I made x6, my first bracket would be +8, my second bracket would be 0, and then the whole thing ends up equaling 0. Yeah, you're essentially finding the inverse for one of the things in the brackets.
So you just it.
Pretty much, yeah. We have 2 minutes left, guys, so I don't think we're going to quite get to the third one. We will finish off that third one next lesson, and in addition to that, I'll get you to do some more practice finding both. because I think that's important. But yeah, on that note, let's pack up.